This webcast talks about quantitative force analysis for situations where all of the forces are parallel to one of the coordinate axes. So we're going to talk about how to identify and quantify all of the forces in a force diagram. So let's look at this first question, which is talking about Ava, the astronaut, and it gives us her mass as 85 kilograms. And so we'd like to know how much she weighs. Her weight is the force of gravity on Ava, and that equals her mass times the acceleration due to gravity where she's located. Acceleration due to gravity is always represented with a lowercase g. Okay, so her mass is 85 kilograms. And it says that she's on Earth, and on Earth, the acceleration due to gravity is 9.8 newtons per kilogram of mass. And so if we multiply those, we see that her weight is 833 newtons. Weight is a force, and it's always measured in standard units of newtons. Then it says, okay, when Ava goes to Mars, what will she weigh there? When she's on Mars, she's on a smaller planet, and so the acceleration due to gravity is different. She's very far from Earth, and so her new weight will be different than her weight on Earth. Her new weight on Mars will be her mass times the acceleration due to gravity on Mars. And so her mass is the same. Mass is fairly constant no matter where you're located in the universe, but the acceleration due to gravity depends on your location because it really depends on the planet that you are closest to. And so when she's near Mars, the acceleration due to gravity is 4.28 newtons per kilogram of mass. And so her weight will be less. It will be only 363.8 newtons when she goes there. Ava's spacesuit weighs 236 newtons on Earth. So could we find its mass? Well, we know that the force of gravity, or the weight, is the mass times acceleration due to gravity on the Earth. So the mass would be the weight of the spacesuit divided by that acceleration due to gravity. So it would be 236 newtons divided by the 9.8 newtons per kilogram, which is acceleration due to gravity near Earth. And so the spacesuit has a mass of 24.082 kilograms. Okay, so now we're able to calculate the force of gravity, or the weight of something. Let's look at this next example. Here we've got two blocks that are stacked on top of each other. They are motionless, right? They're not moving. They're just sitting there on the ground, I guess. And it's asking us to make force diagrams for both blocks and also for the Earth. Okay, so I'm going to do a force diagram for A, and a force diagram for B, and a force diagram for the Earth, which is really the same as the ground or the floor. Okay, so let's start with block A. I usually start with the weight. Block A has a weight because it has a mass. So the force of gravity, or the weight of block A, equals its mass, which is 2 kilograms, times 9.8, which is the acceleration due to gravity on Earth, and so it has a weight of 19.6 newtons. And, the Earth is exerting a force. Oh, I should have written it this way. I'm so sorry. I should have described the force more completely. This is the force of gravity on A by the Earth. And so just like the Earth is exerting a gravitational force on block A, well, block A is exerting a force on the Earth. and this is the third law pair of that, and so it has the same amount of force, but it's in the opposite direction. And so I'll just put a little symbol next to these so that we understand that they are third law pairs. Okay, what other forces are acting on block A? Block A is motionless, so I know that the net force on block A is 0, and so there must be a force that's balancing its weight that goes in the opposite direction, and that's probably the normal force. A is pressed into B, right? They are pressed together, and so that means that there's a normal force on A by B, and it's because B is supporting A. B is holding A in place, not letting A fall down. And that normal force must equal the force of gravity on A by the Earth because these two forces are balancing each other. Since the net force is 0, there has to be as much force going up as there is going down. Okay, where is the third law pair of this normal force? The third law pair has to be the same type of force. It's also a normal force, but it has to be on B being exerted by A. And it's going to be the same amount of force, but it's just pointing in the opposite direction. You could think of it as the weight of A is pressing down onto B. Okay? Let's see, and let's keep going with block B. Block B has a mass of 1 kilogram, and that means that there's a gravitational force on B, which equals the 1 times 9.8, which is 9.8 newtons. And the third law pair of that one is that block B is exerting a gravitational force on the Earth in the same amount. So those are third law pairs. Block B is motionless, so I know the net force equals 0. And there must be some force pointing up that balances these two forces that are pointing down on block B. Since I know that the net force on B equals 0, it must be that there's some force that's supporting block B, right? Block B is pressed into the ground, so the normal force that's being exerted on B by the ground must equal the two forces that are pointing down, which are the gravitational force on B by the Earth and the normal force on B by block A. So if I add, the 9.8 plus the 19.6, I'll get the total of that normal force. It's 29.4 newtons. When I do this, I have as much force going up on B as I have going down, and so all of the forces on block B have balanced, and the net force is 0. Okay, where is the third law pair of that one? It must be going down over here, right? It's the normal force on the ground that's being exerted by block B. It has that same amount of force, but it's in the opposite direction. These are third law pairs. And so there's also a net force of 0 on the Earth or ground. Okay, so we have drawn good force diagrams for all three entities, and then it says, how does the force that block A exerts on block B compare to the force that block B exerts on block A? Well, here's the force that A exerts on block B, and here's the force that B exerts on block A. They are third law pairs. So they're both normal forces, the same type of force. The force that's exerted on A by block B is equal to the negative of the force, the normal force that's exerted on block B by block A. They have the same magnitude, right? They are both 19.6 newtons of force, and they act in opposite directions. They are Newton's third law pairs. Okay. Let's look at another one that's kind of similar, but here we have 3 blocks arranged in a stack on a table. And they've given us the masses of each one. I'm just going to call them like block A, block B, block C, just for simplicity. And someone is pressing down with a vertical force on that top block. And we want to know the magnitude and direction of the normal force exerted by the bottom block on the middle block. So they're asking me about a force that's being exerted on that middle block. And so I need to do a force diagram for the middle block. Which I'm calling B. This is the only force diagram where I'm going to see the forces exerted on B. Okay? So let's see here. I'm going to start with a weight of B because they're giving me the mass. So there's the gravitational force on B by the Earth. And I know how to calculate that now, right? That's the 18 kilograms times 9.8 newtons per kilogram. And so that's 176.4 newtons. Block A is sitting right on top of block B. So the weight of block A is pressing onto B. So there is a normal force here that's being exerted on block B by block A, and that equals the weight of block A. So that's 16 times 9.8. Which is 156.8 newtons. And then also there's this vertical force that someone is pressing down on the top block with, and it just gets passed along. They're touching the top block, but that force gets passed along, and so block B feels it as well. And so there is an applied force on block A by, I guess, the person, and that equals 170 newtons. Okay, so we've identified a lot of forces pressing down on block B. What kind of forces are supporting block B and holding it up? Well, there must be a normal force because block B is pressed onto block C, and whenever two things are pressed together, there's a normal force perpendicular to the surfaces. So C is exerting a normal force on B, and I think because the net force on block B is 0, it's motionless, right? None of these blocks are moving. Then this normal force that C is exerting must equal all of the things down below. Since the net force is 0, that must mean that the normal force that is being exerted on B by block C must equal the 170 plus the 156.8 plus the 176.4, because we have to have as much force going up as we do going down. And so we see that that is 503.2 newtons. And so that is the answer to the question. That's how much force the bottom block must be exerting on the middle block in order to support it and hold it in place. Let's look at an example where we have some forces that are not just going up and down, but also horizontally. Here's Daniel, and Daniel is on a frozen pond, and he's being pulled by a rope to the side here by Kim. And let's see here. So we're going to do a force diagram for Daniel. So first of all, we know that Daniel has a weight. And we can calculate that because we have his mass. And so his weight is 1,029 newtons. It says that Kim is pulling him to the right. So there's a tension force on Dan by the rope, and they're telling us that equals 300 newtons. It tells us there's a friction force that opposes his motion. Well, since he's moving to the right, the friction force must be pointing to the left. And they're telling us that is 205 newtons. And let's see, is there any other force? Well, Dan's weight is pressed onto the ice, and he's not falling through, so the ice is supporting him. So there is a normal force being exerted on Dan by the ice, and it's balancing his weight. There's no movement in the vertical direction, so in this direction, vertically, the forces are balanced. And that's how I know that the normal force and the gravitational force are equal to each other. Okay, so what is the net force? The net force in the horizontal direction, the net force in the vertical direction is 0. And that's because there's no movement in that direction. So his velocity is constant in the vertical direction, okay? But in the horizontal direction, he is moving, and I don't know if he's moving at a constant velocity or not yet, but let's find the sum of the forces in the horizontal direction. I'm going to add the force that goes to the right, which is the tension force, and then I'm going to subtract any forces that go to the left. There's only one, there's the friction force, and so that is going to be 300 minus 205. So the net force is 95 newtons to the right. Right? There's more force to the right than there is to the left. So that is the net force on Dan. And since there is a net force, I know that Dan's velocity is changing. Because the net force is not 0. And I can even be more specific than that. Dan's velocity is to the right, and because the net force is to the right, acceleration is also to the right. When the acceleration and velocity vectors point in the same direction, the object speeds up. So Dan is speeding up as he moves to the right.